Welcome to the next session on cloud computing and gaming and mobile and power management. So actually it's a very rich session, rich on content and rich on methodologies. The first two papers are rather experimental one and implementation oriented. The third one is a theoretical one. However, I missed the authors of the... Are still some people from the third paper here? Yeah. Okay, so you are the speaker. Okay, so now let's introduce me the speakers of the first paper, because the first paper will be presented by two assistant professors. The first one is Cheng-Sin Su from the National Tsinghua University, and the second one is Chan-Yin Huang from the National Taiwan Ocean University. The topic is the introduction of the system GamingAnywhere, which is an open cloud gaming system. So I assume that after your talk, the most important question will be, how can I download it?
Thank you for the introduction. So today I'm happy to present our work on GamingAnywhere, which is an open cloud gaming system. This is a joint work with Professor Huang, who is going to present the second part of give the second part of the talk, as well as Professor Quanta Chen, his student Yuchen Chang. Okay. So this paper is about cloud gaming systems. I want to start with why do we need a cloud gaming system? So I claim that we gamers' life is miserable. And there are so many reasons that our life is miserable, at least 3 of them. Just as example. So first of all, modern games are getting so complicated or complex. So setting up the game actually takes a long time. And also configuring a game takes a long time. Okay. Actually, I can give an example. Before I came to the conference, I checked the weather online, and I found in Oslo the weather is like temperature is like -10 Celsius. So I think I'm going to play some game. So I took my StarCraft 2 and tried to install it set it up on my MacBook Pro. I don't know whether I should thank Apple or thank Blizzard. It took me half day to install the software before I can play StarCraft 2. That's a very long time, especially if I just want to test the game. I'm not going to spend half day to set up the game and try it. Okay, so that's the first problem. Second problem is many games are only compatible with certain operating system or certain hardware. So some games may only run on Windows. Some games may require a specific graphic card, a level of graphic card to run. Okay, and the third problem is to play the latest game. Oftentimes we found ourselves we have to upgrade our system in order to play them, and in some cases. For example, my MacBook Pro, actually I cannot upgrade it because it's a laptop, okay? So there are so many issues, that's why we need cloud gaming. So what is cloud gaming after all? So I want to use this figure to show you the idea. On the left-hand side, we have a bunch of powerful game servers hosted in data centers. And we're going to run the game on these servers. So these servers are very powerful, so they can do the game with all the details turned on at the highest possible quality. So after the game renders the game scene, we will capture the image as well as the audio. We will do real-time encoding, okay? And then we will stream the audio and video data over the internet to a bunch of players on the right-hand side. So the player can use a thin client to play the game. The player can use different type of devices, including a desktop, a laptop, or mobile devices. Okay, so this is called cloud gaming. One thing we don't show in this figure is clearly that the player needs to input something. So there will be a reverse channel connect from the thin client back to the game server, sending all the keyboard and mouse events. All right. Cloud gaming sounds like a good idea for different parties. From gamers' perspective, there are quite a few advantages. First of all, we don't need to upgrade our server, our PC anymore. Okay, Second thing is that we wouldn't have a we wouldn't suffer from the high overhead of setting up the game, like my example of StarCraft 2 on MacBook Pro. It took me half day to do that. Okay, and the third thing is you don't need to set up the game on all the computers. You just turn on your computer, launch the thin client, connect to the game server, and now you can play game anywhere, anytime, as long as you have the internet access. For the game manufacturers, they also like cloud gaming because, first of all, they don't need to develop different versions for Windows, for Mac. They just develop one version because the computer in the data center is going to be a Windows or a Mac. All right? It also reduces the production cost. They don't need to print the box, produce the DVD, and most important of all, there will be no parity because no one gets the real game, right? Because they connect to the data center to play it. All right, and cloud gaming is actually growing according to market study. There is a market study indicating that in the next 6 years, the revenue of cloud gaming will increase 9 times. Okay, and we do see quite a few startup companies doing cloud games. This includes probably the well-known one, OnLive in California. This icon belong to a software called StreamMyGame, and in our paper we compare against OnLive and StreamMyGame. Okay, and there are some other companies. There's a company called Gaikai, also doing cloud gaming and quite successful. In fact, a few months back, Sony Entertainment actually acquired Gaikai because they found a huge potential of online gaming. Okay. So this sounds great. If we apply online gaming, then we will have a lot of advantage. So what's wrong with the current online gaming technology? There are still quite a few limitations. So I'm going to use OnLive as an example. So the first limitation is bandwidth requirement. OnLive requires you to have at least 5 megabits per second to play their game. And this is not high definition resolution, this is standard resolution. Okay? Another limitation and more serious limitation is that OnLive require you to live close enough to their data center so that you can play the game. Okay? Because as we know, the response time is a very important performance metrics for real-time applications such as computer games. Okay? There are many more limitations of current online gaming system. And we as researchers, we have tons of ideas that we want to apply to online gaming system to enhance, to improve the performance. Okay? But there's a problem here. Most of the existing online gaming platforms are proprietary and closed, so we can not test our idea on them. Okay? That's why we introduced the platform. We call it GamingAnywhere. To our best knowledge, GamingAnywhere is the first cloud gaming platform that is open to researchers, service providers, as well as end users. We have 4 design objectives when we start to develop GamingAnywhere. The first thing is we designed this initially for researchers. So we want to have high extensibility. If a researcher doesn't like our, for example, RTP library, he or she should be able to take out our RTP implementation and replace with a new RTP stack. Okay? Portability. We implement our thin client on 4 different operating systems: Windows, Linux, OS X, as well as Android. We also implement our server on some of the systems, but not all of them, especially Android. We haven't done that yet. Configurability, we allow the user to explore, to try different configuration, different setting, and observe how would that affect the performance of the cloud gaming system. And of course, openness, so that everybody can try it. Okay? This is a high-level architecture of our system. I will start from top, which is the game servers I mentioned earlier, hosted in data centers. These are powerful servers running the actual game. Okay, so the real-time audio video stream will be sent from the game server to the client and user at the lower right corner, and these users use thin client to access the game, to play the game. Okay, there will be interaction between them. But there is yet another server that is required in our system, which we call it portal server. Portal server is the entry point for the user. So user log on to the portal server, see what are the available games, and they may choose which game they want to run, okay, they want to play, and portal server will connect the game server and launch the corresponding game for the user. Okay, so this is the high-level picture of our system. So I'm going to hand over the presentation to my colleague.
Good afternoon, everybody. I'm Jun Huang from National Taiwan Ocean University, and I'm going to talk about the implementation and the performance numbers of the GamingAnywhere system. Basically, we focus only on the game server and the game client, as we show in this figure. So you can see that there are two connections set up between the game server and the game client. One is the data flow connection, and another is the control flow connection. Basically, we use the data flow connection to deliver our encoded audio and video frames through the RTSP and RTP protocol. And for the control flow connection, we use this connection to send our control events from the game client to the game server. And basically, we did not leverage any existing protocol, but we implement our self-implement protocol to implement the control flow connection. So you can see that by following these two connections, there are a lot of modules, and we implement these modules using basically many open source packages. So this is the implementation overview of our server and the client modules. Basically, the system core is majorly implemented as a library, and we also provide a lot of modules, and the video source, audio source, encoders, replayers, and the RTSP server. And for the client modules, we have RTP client, decoders, controllers, and the renderers. And these three projects is the most important open source package to our system. We use the FFmpeg, the live media, and the simple direct layer to implement our system. And if you want to know the relationships between the server components, here's for server part. We can classify all the modules into 4 categories. The first is the RTSP server thread, and the second is the modules to handle audio frames, and the third is the modules to handle video frames, and the last is the module to handle user control events. So today I'm not going to introduce the detail of all the modules, but what I'm going to talk about is how we process video frames in this part. So when GamingAnywhere is going to process video frames, basically we have 3 basic fundamental steps. The first is that we have to capture the game screen, and then we pass the game frame to the converter. The converter is used to convert the pixel format from RGB to YUV, and finally the converted frame is sent to the encoder to encoding and sent over the network. So a straightforward to implement this system is to, well, we can write all the modules in the same thread. But this is not an efficient method, because we can estimate the overall frame throughput by this formula. That is 1 second divided by the summation of all the 3 delays. Oops, I forget to introduce the 3 delays. So we have, suppose we have different processing time for different modules. So there are T capture for the capture, and the T convert for the converter, and the T encode for the encoder. So we have different processing delays for different modules. So we just talk about that the overall frame throughput can be obtained by the 1 second divided by the summation of the 3 delays, 3 process times. So if we have a summation of 40 milliseconds, the maximum available frame throughput is less than or equal to 25 frames per second. So we adopt a pipeline design to improve the parallelism. So actually, we implement the 3 modules in 3 different threads. So the first thread will capture the frame and then pass to the second thread to do the color space conversion. And then finally, the frame will pass to the video encoder to do the video encoding. So in this case, we can improve the frame throughput to 1 second divided by the maximum of the 3 delays. So if the maximum delay from the 3 component is 20 milliseconds, so we will improve the frame throughput to achieve at most up to 50 frames per second. So I think this is the most important part in our GamingAnywhere server. As to the client, we have 2 modules. The one is the RTSP client, and another is the main thread. Basically, the RTSP client is used to receive encoded audio frames and video frames, and the main thread is used to capture the user event at the client side and transmit the client to the server side. And also, I'm not going to introduce the detail of these 2 modules, but I think the most important is that we use a single frame buffering strategy to shorten the response time of our system. So suppose that we know a video frame can be split into different number of packets. So since we are going to buffer for only 1 frame, we have to know how many packets are burned to the same frame. So in this case, we can see the below figures. This is a sequence of RTP packets, and you can find that the RTSP protocol actually will have a marker bit to indicate that this packet is the last packet of a frame. So based on this heuristic, we are able to know that, okay, the first 3 packets belong to frame 1, and the 5 packets belong to the frame 2. Okay, so we can achieve the goal of buffering for only 1 frame. So based on this heuristic, we can also to estimate the required buffering time of the system regarding the playout. So if we have a frame of size 30 kilobytes, and the frame is transmitted under a 50 megabit per second network, so we can estimate that the buffering time for playout is roughly 5 milliseconds. Okay. Okay, so here are some screenshots that we show to you, and you can find that the left top screen is our server running in a virtual machine, and the rest 3 screenshots is for clients running on Windows, on Mac, and on Android. And we know that watching this screenshot cannot satisfy you, so we have prepared a live demo for you. Okay. So we have set up a server running here. Okay, I can show you that. We have 2 laptops in front of the desk, and this is our server. We use a Limbo game. Okay, and then I will run the client on another laptop, which is I used to present paper. So I have to switch to the command prompt. Okay, so this is actually a beta version of our client. So we have a command RTSP play.exe, and we have a configuration to specify the configuration of the game on the server. And also we have a URL to connect to the game server. So we don't use wireless connections. Actually, we have a crossover table here to connect these 2 laptops. And we use a private network to make the notebook in the same local area network. So now I'm going to connect to the server. Okay. Okay, because of the resolution is basically HD, so the screen is not able to show the entire screen of the game. But actually, you can see that although it is not normal, but actually you can control your game on the game server. So I can press any key to start. But actually, I should do this in front of my client, not on server. So now I'm going to hand off to the client side. So I'm going to choose a chapter. Okay, and maybe this one. And you can see that is avatar here. I'm going to control here, move left, move right, and I would like to pull this car. Okay, jump over it. Oops, I'm not familiar on game playing. Maybe I have to run for a short distance and jump. Oh, that's pretty good. Okay, jump over the rope and move down. Okay, so you can see that it looks smooth. Okay, so okay. Maybe I should turn this monitor for you to see how it performs on the game server. So I hope my notebook would not drop down. Okay. Ooh. Yeah, that's fine. Okay, so you can see that the screen should be synchronized. Okay, so I run pretty slow. Oh, okay, there's a ship I can take on the ship. Okay, and then jump, jump. Oh, oops. Okay, that's all. Oh, thank you. Okay, let's back to the slide. Okay, so we just see the live demo. And now I'm going to talk about the performance numbers of GamingAnywhere. And we compare our system against OnLive and StreamMyGame. Also, this is the environment we conduct our experiments. So you know that OnLive is an internet service, but both GamingAnywhere and the StreamMyGame are local applications installed on a local computer. So to make it a fair comparison, we use a FreeBSD to run a traffic shaper to ensure that the network environment between the OnLive and the StreamMyGame are similar. And we also run another client in a local network to access the 3 different platforms. Okay, and the performance, the configuration of a GamingAnywhere server is as follows. We use the LAM MP3 encoder for the audio, and we use the X264 encoders for the video. And we know that X264 is a complicated encoder, and it has a lot of parameters to configure. So this is the parameters we use for the X264 encoder. And if you would like to know how we choose this performance, you may read our paper. We have an appendix at the end of the paper to describe how we choose these parameters. So the first performance metric we are going to examine is the process delay of the system. Basically, we want to measure the process delay at the server, which is defined by the timing that the control event is sent to the server until the corresponding frame is generated from the server. So basically, it should be T2 minus T1. And we are also going to look at the playout delay, which is the timing that the client receives the encoded frame and the timing that is actually shown to the user. So the playout delay is basically defined by the T4 minus T3. Okay, of course there's a network delay, but in this paper we did not discuss about the network delay. So this is the measurement result for the 3 different platforms, and we can show that we have relatively quite low delay compared to the other 2 systems. We evaluated the response delay using 3 different games, the Batman, the Fear, and the Doe, and you can see that for the process delay, we are very low, and the playout delay is, looks a little bit similar, but it's still lower. And if we decompose the delay of GamingAnywhere, since we have source code, so we can able to insert some counters into the code and measurement the delay. So at the server side, we have processing delay, and it is composed of memory copy, format conversion, video encoding, and the packetization. And you can see that most of the delays are contributed by the encoders, and the second one may be contributed by memory copy. Actually, the memory copy does not only do the memory copy, but it will lock the video RAM first, and then copy the video RAM from video RAM to the memory. So based on our experience, we found that locking video RAM is a very time-consuming operation. So this is why the memory copy is consumes a lot of delay. As to the playout delay, we can see that our 1-frame buffering strategy is pretty good. So the buffering delay is only for 1 or 2 milliseconds. And the rest of delays seems equally contributed by the decoder and the renderer. Okay, so we also measure the network load of GamingAnywhere. And you can see the upper 3 features are for uplink, and the lower 3 features are for downlink. For the uplink, we only send control events in the uplink, so you can see that the bitrate and the packet rate is not so fast. But we don't know what data are delivered by OnLive and SMG in the uplink traffic. And for downlink bitrate, since our GamingAnywhere system is configured to run at a bitrate of 3 megabits per second, so you can see that the performance for downlink is roughly meet the configuration. Okay, and we have to note that the screen resolution we use is HD resolution. And this is for the video quality, and you can see that we use the PSNR and SSIM index to compare video quality. And you can see that in most cases, our quality is better than the compared two systems. Okay, so I think the most important question is here. Are we going to release this system to the public? Actually, we have set up a website, and this is the URL. And you can see that there is a download link. But please note that this link does not work now because most of authors were kidnapped by this conference. So it should be available when we are back to our country. And we are planning to release the code to the public in maybe March or April. Okay, so here I make a short conclusion. Basically, GamingAnywhere is to our knowledge, is the first open cloud gaming system. And our measurement result shows that the system outperforms OnLive and StreamMyGame. We have around 60 to 90% of processing delay reduction and 3 to 19 decibel video quality improvement. And we believe that there is a lot of research topics on cloud gaming, and we hope such an open system is able to stimulate more studies and applications on cloud gaming. Okay, my talk's finished here. Thank you.
Perfect. Thank you very much. Questions?
Hi.
Hi.
Thank you very much for your talk. Did you try to host several instances of GamingAnywhere in one server?
Currently, we don't. We are planning, but currently we do not have host services, so we just focus on the server and client. But actually, we are making some research on installing a server on virtual machine and run it as a service. But we are still working on that.
Okay, next question.
Thank you for your talk. Very interesting. Actually, I'm now that I look at the figures, I'm rather surprised at. I'm more surprised at the fact that OnLive and SMG do so bad than I'm at the fact that you do so good. Do you have any idea why your performance is so much better than theirs?
Oh, that's a good question. We did not compare our system against OnLive and SMG, but I think the parameter to the encoders is maybe one factor because we don't know how they tune their encoders. And maybe buffering is also another factor to improve because we only buffer for one frame. So maybe that's because we have a shorter response delay.
May I add a remark, because that's actually my question as well, because this is in a sense also missing from your paper. So you should invest more work on really explaining.
Okay.
So just showing you are better with figures, it's nice, but we would like to understand it. Obviously, you also would like to understand.
Okay.
Just a quick comment. It's probably that on their servers they are running multiple games, whereas for yours you have dedicated.
Oh
servers.
yes. That's a good point. Actually, we are writing a new paper to discuss if we run multiple games in the same machine. Basically, we may run this system in virtual machines, maybe 4 games or 3 games, 4 games in the same machine. But we have not finished this work. Maybe it will later.
I'll make it quick. I think that's the point. I think calibration is an issue here because you don't really know what's happening on the OnLive cloud, right? So how can you actually really make a really fair comparison because you don't know what the load factor is in OnLive while you compare it to yours, right? Because you cannot. What would be great, I assume, if that would be possible, is get an OnLive image, run it on your server, and run your image, and then compare it. I know that's not working, but maybe you can think about how you can more calibrate it, I guess.
Yeah, actually, we have a paper in 2011 published in a multimedia conference to discuss the measurement study of how to measure response delay for the OnLive the platform, because it is hosted in a remote site. So, well, maybe we can. What we can do now is try to simulate, to set up a similar environment to measure the result. But maybe we can try this idea later in the future.
Okay, I allow myself to put the last question. Can you imagine to use, maybe not just now, but later, GamingAnywhere for something else than gaming? For example, cooperative annotation of videos or images?
But I'm not quite sure the question.
Have you thought of using this software for something else than gaming, like a serious gaming, like common cooperative annotation of videos or images?
We have not tried in other applications, but we have tried to streaming desktops to the users, and for the rest of